announcing?
Tim, what are the announcing?
Some people
Tim, what are they announcing today? Oh.
white smoke.
All right, well, I have the great pleasure of introducing our faculty candidates today. Dr. Andrew Lowy comes to us all the way from the wonderful state of Wisconsin, where he is currently a postdoctoral associate at the Wisconsin Institute of Discovery, working with Steve Wright. He earlier received his PhD in applied mathematics from USC, and has a very interesting sort of academic and work background with undergrad degrees from Princeton in public policy, and then training working in the private sector, additional training in mathematics, and he sort of, I hope, and I assume he's going to be telling us about how he brings all of those things together, sort of the technical mathematical side with sort of the public policy side in his seminar talk today, so we're really looking forward to it. Thank you, Andrew.
Thank you for that nice introduction, and thank you all for being here today. It's a privilege to speak before such a distinguished group. So to begin, I'm going to tell you a little bit about my unique background. So I started with a degree in public policy from Princeton, where I was trained mainly in economics and completed theses exploring the intersections between economic policy and health policy. And after graduating, I worked in industry and management consulting, working on life sciences and healthcare companies for a few years, before going back to school and studying math at Columbia, where I took advanced undergrad and PhD level courses. And then I went to USC for my doctorate in applied math, where I passed qualifying exams in numerical analysis and optimization, probability, real analysis, and statistics and machine learning. And during this time, I also began my research with Meisam Razaviyayn in the ISyE department at USC, working on optimization and machine learning. Started with a project on min-max optimization before transitioning to differentially private optimization, and also working on algorithmic fairness in machine learning. And currently I'm a postdoc here in Madison, working with Steve on optimization and machine learning, again, DP optimization as well as robust. And so I actively contribute to these three research communities: optimization, machine learning, and privacy. And while my research so far has mainly leveraged my math background, optimization, machine learning, as I'll talk about at the end of this talk, I do plan to incorporate my public policy background in my future work. So with that, let's get started with the content of this talk. As the title suggests, I'll be talking about the foundations of private optimization, which is a critical area in modern machine learning. So to begin, let's look at why data privacy has become such a pressing concern in modern machine learning. So organizations are increasingly relying on highly sensitive data, such as personal health records or GPS coordinates, to make critical decisions in sectors ranging from healthcare to transportation. For example, hospitals may use optimization algorithms trained on sensitive patient data to determine how many resources to allocate to different units, or to personalize treatments through machine learning models. And while these models can be extremely useful, they also introduce a serious risk: the potential for individuals' private data to be exposed, violating those people's privacy. For example, in a well-known case, an attacker was able to re-identify the medical records of the Massachusetts governor by linking anonymized medical encounter data with publicly available voter registration records. So this example illustrates that even anonymized data is not safe against linkage attacks. And the stakes are high. Organizations that fail to protect the privacy of their data risk violating laws such as HIPAA in the US, the GDPR, and the AI Act in Europe, as well as many other countries around the world, which can impose steep fines for privacy violations. Yet, protecting data privacy in the age of machine learning is far from straightforward. So research has shown that machine learning models themselves can leak their private training data. For example, researchers recently showed how to extract private training data from ChatGPT. So just by conversing with ChatGPT and entering the right prompts, they were able to get ChatGPT to spit back some verbatim text that it had memorized in this case containing the contact information of a real person, JAL, whose data was used to train the model. And this isn't just a problem for large language models. Indeed, all machine learning models are fundamentally vulnerable to a wide range of privacy attacks. So how can we train ML models without leaking individuals' data? Or more generally, since training a machine learning model amounts to solving an optimization problem to find the model parameters with small error, how can we solve optimization problems without leaking individuals' private data? To tackle this, we'll turn to differential privacy, which offers a rigorous framework for enabling us to learn without leaking. DP is the gold standard of rigorous data privacy notions, and its inventors received the Gödel Prize in 2017. To define DP, consider a dataset X with data from n people, x1 through xn. And suppose this dataset is used as input to some algorithm M. Now consider a counterfactual world where person xn's data was never collected, and we instead feed this adjacent dataset x prime into the algorithm M. And from a privacy perspective, we would like for these outputs m of x and m of x prime to be similar. Okay, because if this were the case, it would be difficult for an attacker who observes the output of the algorithm to even guess whether person xn's data was used at all. And in particular, this would make it very hard for the attacker to make inferences about the properties of person xn's data or to reconstruct that data. In order to accomplish this stability of the algorithm M, it's going to be necessary to introduce some randomization or noise into the algorithm. Thus, m of x and m of x prime become random variables, and differential privacy requires that the probability distributions of these random variables be close together. Okay? More precisely, we say a randomized algorithm M is epsilon delta differentially private if for all pairs of adjacent data sets x and x prime, and all events S in the probability space, we have this inequality holding. So here epsilon and delta are the privacy parameters, quantifying how much privacy we get. Okay, so as epsilon and delta get smaller, this inequality gets tighter, and it becomes more difficult for an attacker to infer the presence or absence of any individual's data. And for strong privacy guarantees, it suffices to consider epsilon as a small constant, such as 1, whereas delta should be very small relative to the number of data points. And DP has by now been deployed by many organizations, including Apple, Google, and the US Census Bureau, to name a few. Are there any questions about differential privacy? This is probably a new definition for many of you, so feel free to ask anything.
You say it's deployed, what does that mean?
They've used it in the actual products, or the US Census Bureau actually
So they
used it.
ensure that their products are epsilon delta private for some values of epsilon.
Yes.
Okay.
Yeah. Not all of them, not all their products, but some of them, yeah. Any other questions? Okay. So my work bridges two traditionally distinct fields, the field of differential privacy and the field of optimization, and centers around the following question. How can we develop optimization algorithms for training machine learning models that are differentially private without sacrificing more accuracy than necessary? In answering this question, I draw on both theoretical and empirical methods. So rigorous theory is absolutely critical in private machine learning because it's not enough to simply hope for privacy, particularly in applications involving highly sensitive data. Theory offers provable guarantees that our methods will preserve people's privacy, and it allows us to tailor the definition of differential privacy to each specific context or application. It's through theory that we can understand the fundamental trade-offs between privacy and accuracy, as well as the computational efficiency of our approaches. And these theoretical insights are crucial because they guide and inform the practical applications of the methods that we develop. On the flip side, practical applications are what drive and motivate my theoretical work. Through collaborations with companies like Apple Machine Learning Research, Google Research, Meta, and Mitsubishi Electronic Research Labs, I gained a deeper understanding of the practical challenges that companies face when deploying optimization algorithms and machine learning systems in complex real-world environments. And these collaborations have directly inspired many of the problems that I've worked on. Additionally, I conduct rigorous numerical experiments to validate the performance of my methods, and some of my algorithms related to fairness have already been deployed in industrial settings, confirming the practical relevance of my research. Now, before detailing my contributions, let me give a brief overview of prior work on differentially private optimization for machine learning. So in 2014, Basili, Smith, and Thakurta characterized the minimax optimal error rates for differentially private empirical risk minimization, also known as finite sum optimization with convex Lipschitz loss functions. Note that without privacy constraints, the optimal error for this problem would be 0, because we could get arbitrarily close to an exact minimizer, for instance, by running enough iterations of gradient descent. But such an algorithm would not be differentially private, because we know that randomization or noise is necessary to satisfy DP. So in fact, BST's optimal algorithm for DP-ERM was a noisy differentially private variation of gradient descent. In 2019, Basili and a different group of co-authors determined the optimal rates for DP stochastic convex optimization, which corresponds to minimizing expected population loss or test error in machine learning. And in 2020, Feldman, Korn, and Talwar gave linear time algorithms that achieve optimal error for DPSCO with sufficiently smooth loss functions. Now, although these are important contributions, these results rely on a number of simplifying assumptions. So first of all, they assume that all the data in the data set is private, that we're given an a priori bound on the values that our data might take, and that the worst case Lipschitz parameter of the loss function is uniformly bounded over all data points in the universe. It's also assumed that the loss function is convex, that data is centralized, stored all in one place, and accessible to the learner at every iteration, and no other requirements beyond privacy are considered. And while these assumptions are convenient for proving theoretical results, unfortunately they often fail to hold in practice. For example, in practice we may have side access to public data. This could be data that was generated synthetically or that comes from people who waive their privacy rights and sell their data, and we'd like to be able to leverage this public data to improve the performance of our model while still maintaining the privacy of the private data. Additionally, we often lack an a priori bound on our data distribution, right? We're given a data set, we don't really know what distribution it came from. Our data can contain outliers or even heavy tails, causing the worst case Lipschitz parameter of our loss function to be unbounded and rendering previous results not applicable. Additionally, we often encounter non-convex objective functions, as in deep learning and many other applications. And our data is often decentralized, stored locally on people's devices or by organizations such as hospitals, banks, or schools, and this makes the optimization more challenging. Finally, we may have other requirements beyond privacy, such as ensuring fairness of our model's predictions with respect to different groups, or robustness in the face of adversarial attacks. And my work has tackled all 5 of these practical challenges in differentially private optimization. An important contribution to my work is in understanding the fundamental limits of performance. That is, I characterize the minimax optimal error rates for practical DP optimization problems, such as DP optimization with side access to public data, with outliers or heavy tails and unbounded worst case Lipschitz parameter, with non-convex loss functions, with decentralized data, and so on. And characterizing the optimal error rates involves 2 major components. So one, I develop novel algorithms and prove privacy and accuracy guarantees for these algorithms, which gives us an upper bound on the achievable error for a given problem. And secondly, I prove fundamental minimax lower bounds to show that no other algorithm can possibly perform better than my algorithm for the given problem class. And second, my algorithms are not only minimax optimal in terms of their error, but they're also scalable, running efficiently even for huge models and data sets. And third, my algorithms are practical, in many cases outperforming the state-of-the-art methods in numerical experiments. Now, for the rest of this talk, in the interest of time, I'm just going to focus on one of these problems, namely DP optimization with decentralized data. How can parties learn a collaborative model without sharing their sensitive data? The federated learning paradigm proposes that parties store their data locally, and instead of exchanging this raw sensitive data, they would instead exchange focused updates. And so this is often done with the help of a central server, so that over the course of many rounds of communication, the parties would send messages to the server, which are functions of their local data set, and then the server would aggregate these messages and update the global model. And this process can repeat for many rounds until we arrive at a model that performs well for all of the parties involved. And an important motivation for the introduction of federated learning was privacy, because of intuitively decentralized local storage should be better for privacy rather than all the parties, sharing their sensitive data. And while this is indeed somewhat true, unfortunately, merely storing data locally is not sufficient to prevent data from being leaked. And that's because the messages that are sent from, for example, from hospitals to the server can leak private information about the patients in that hospital, as can the global model parameters, which are often stored on the server during federated learning. For example, in this paper, we acted as the adversary and showed how to execute a gradient inversion attack against a federated learning model. So here, the parties collaborating were each devices holding image data of a different celebrity, and even without accessing this person's sensitive raw data that was held locally on their cell phone, just by observing the gradient of this person's loss function, which was communicated to the server in standard federated learning, we were able to use that gradient as well as the global model parameters to invert the gradient and reconstruct an image of this person, violating her privacy. So this shows that we need some additional safeguards beyond local storage in order to prevent data from being leaked during federated learning. To that end, we'll consider differential privacy, which can actually provably prevent leakage. The next question is, what type of differential privacy do we need in the context of federated learning? So clearly this question the answer is going to depend on the application area that we're interested in. Let's focus on the setting for now of cross-silo federated learning, where we have the parties collaborating are organizations typically, such as hospitals, banks, or schools, each containing data points from many different individuals. This is in contrast to the cross-device federated learning setting, where each party collaborating is a device just having data from one person. Okay, I'll touch briefly on the cross-device setting at the end of this talk, but let's try to figure out a practical privacy notion for the cross-silo FL case for now. So assume for concreteness, just to have a running example, that we have a network of hospitals that are trying to collaborate to solve a distributed optimization problem or train a machine learning model together. And we'll assume that a patient only wants their own hospital to know their own data, but that patient is not willing to reveal their private medical records to other hospitals or to the server or anybody else outside of their own hospital. And so we'd like a notion of differential privacy that prevents data from being leaked to the untrusted server as well as to other hospitals and other third parties. So this implies that the local updates that the hospital send to the server should satisfy differential privacy to prevent gradient inversion attacks and other attacks. At the same time, we also want good accuracy. So we don't want a notion of differential privacy that's excessively stringent. So with those criteria in mind, let's take a look at previously proposed notions of DP for federated learning and see what their shortcomings are. So central DP requires the final output of the optimization algorithm to satisfy differential privacy. So this protects against an adversary who observes the final trained machine learning model or the predictions of the model, but it does not protect against an attacker who's able to eavesdrop on the communications between the hospitals and the server, or who accesses the global model parameters on the server during training. Thus, central DP is too weak for our setting because it allows data to be leaked to the untrusted server. On the other hand, local differential privacy requires patients to randomize their own data before giving it to their own hospital. So this protects against an adversary even within a patient's own hospital. Okay? So this provides a very strong privacy guarantee, right, ensuring that the patient's data is private even with respect to their own doctor, and in particular this implies that the messages that are sent from the hospital to the server are also differentially private. But the downside of this is that it comes with very poor accuracy because of this stringent patient-level randomization requirement. So we'd like a notion of differential privacy that's intermediate between these two extremes, offering stronger privacy than central DP and better accuracy than local DP. To that end, we propose inter-silo record-level DP, which requires the full transcript of hospitals' sent messages to satisfy differential privacy. So this protects against an adversary who eavesdrops on the communication channels or who has access to the central server during training. So the interpretation of ISRLDP is that it guarantees a hospitalized local data cannot be leaked, even if the server and other hospitals collude to try to decode the data of a patient in hospital I. So it provides a very strong practical privacy guarantee for this cross-silo federated learning setting. At the same time, it's less stringent than local DP because we're not requiring patient-level randomization, and hence we get better accuracy than local DP. Any questions about inter-silo record-level DP or the other two privacy notions, central and local DP?
Is the epsilon and delta, like, that could be different at the different hospitals, so that sort of implies a different notion of differential, I mean, somehow, like, I see that it could still be differentially private at the server, but maybe not at the same level as if the information was sort of aggregated together in different ways. Is that true, or?
That's true, yeah. This definition allows for each hospital to have their own epsilon I, delta I. Yeah.
But does that imply some sort of centralized differential privacy as well, with the sort of a different epsilon and deltas?
Yeah, that's a good question. I don't know if there's like a type conversion between like that depends on like the different epsilon I's, but we know that in general, if like all the epsilon I's are the same, then inter-silo record level DP implies central DP for the same epsilon.
For the same epsilon.
Yeah.
Okay.
And yeah, so local DP is the strongest. Then that implies inter-silo record level DP. That implies central DP, all for the same epsilon. But as we'll see, there's a little bit of a, that's not like the link between inter-silo record level DP and central DP is not exactly tight. You can actually, with some additional structure, some shuffling structure that I'll talk about a little bit later, you can actually get a tighter conversion where like epsilon delta in ISRL DP goes to like epsilon over square root of n in central DP, where n is the number of messages that you're aggregating. Any other, yes?
So going back to your, recovering those images.
Yeah.
I know there's another paper on this deep linkage from gradient, which
Yes.
kind of generates those dummy gradients and matches it.
Right.
So what is your technical approach to do this?
Yeah, so it's kind of similar still, the gradient matching approach. The main like novelty of that paper was that we were doing the gradient inversion attacks in the user, in the federated learning setting where each, where you have a batch of data points and you're trying to sort of reconstruct a representative image from that batch, which makes this a little more challenging. So we used like a diffusion model. We trained a diffusion model to sort of solve the inverse problem, the gradient matching problem, to go from gradient to data. Yes.
Yes, when you talk about the accuracy and the privacy,
Mhm.
so do you think these two are more like a trade-off, or you can make its privacy in the meantime, the accuracy as the central DP?
Yeah, so we'll see that there are fundamental trade-offs that you have to sort of pay a price for differential privacy in whichever differential privacy notion that you're going for. There is a price, and the price depends on how stringent the notion of DP is.
Okay.
So yeah, we'll see like a separation in terms of the accuracy that we're able to get with ISRL DP versus local DP, for example.
It's more like you find the optimal point between these trade-offs.
So like once you fix a privacy notion that you want, say I'm using hospital, so inter-silo record level DP seems practical. Let's then how accurate can we want to satisfy epsilon delta DP? How accurate can we make this thing? And so yeah, my work is sort of trying to discover algorithms that achieve the optimal accuracy for this problem.
Thank you.
Okay, so let's formalize our problem setting. We'll consider n silos, each containing m data points, and these local data sets xi are drawn from some unknown distributions pi. So let f be a convex L-Lipschitz loss function defined on a convex parameter domain in d-dimensional space with bounded L2 diameter. And the data universe X here can be any set whatsoever. Siloized local objective is given in stochastic optimization form with respect to their local distribution pi. And our goal is to solve this federated learning problem while also maintaining privacy. A fundamental question is, what is the minimum achievable excess risk subject to inter-silo record level DP requirements? So here, F star denotes the minimum value that F can take. W private denotes the output of an epsilon delta ISRL DP algorithm. And the expectation is taken both over the internal randomness of the differentially private algorithm and also over the random draw of data X from the distributions pi. And a more precise formulation of this question is, what is the minimax optimal excess risk, where the problem class consists of all convex L-Lipschitz federated learning problems defined on a parameter domain of diameter R, and the algorithm class consists of all epsilon delta ISRLDP algorithms. And our first contribution is a complete answer to the question on the previous slide. So we characterize the minimax optimal error rates by developing novel algorithms and proving tight lower bounds that illustrate the optimality of our algorithms. Second, our algorithms are not just optimal, but also scalable and efficient, coming with strong communication complexity and gradient complexity guarantees. And additionally, our algorithm has state-of-the-art empirical performance in numerical experiments. So to begin, let's look at a simple algorithm for intersilolar record level DP federated learning. This algorithm is a noisy differentially private variation of classical distributed mini-batch SGD. So I'll walk you through how this works. It runs over the course of T rounds of communication. In a given round R, the server is going to broadcast the current global model, WR, to all the hospitals, and then the hospitals are going to use their local data to improve the model. So they're going to draw K data points from their local data set at random, where K is an algorithmic parameter that we get to choose. And they're going to compute a stochastic mini-batch gradient using those K data points. And then they're going to add Gaussian noise, UI, to their stochastic mini-batch gradients. And the variance of this Gaussian noise is carefully calibrated to ensure epsilon delta ISRLDP. Next, these noisy stochastic mini-batch gradients get sent to the server, and the server averages them and then takes a step of stochastic gradient descent, or projected SGD in the case of constraints. And so this algorithm repeats for T rounds, and at the end of the day, we output the average iterate, or in practice, we could just take the last iterate. Now, it turns out that this simple algorithm is actually optimal in terms of excess risk. So we prove the following upper bound theorem. There exists a choice of algorithmic parameters such that noisy mini-batch SGD is epsilon delta ISRLDP, and it achieves the following excess risk bound. So here I'm assuming that the Lipschitz parameter and constraint set diameter are both equal to 1 for simplicity, but you can see our paper for the precise scaled bounds with the proper units. So looking at this bound, we see that it decomposes into two terms. The first term is the optimal non-private statistical rate. For example, stochastic gradient descent achieves this rate. And the second term is the price of privacy, which illustrates the privacy accuracy trade-off. So as epsilon and delta get smaller, we get stronger privacy, but our excess risk becomes larger. In our proof, the first term corresponds to the generalization error of our noisy mini-batch SGD algorithm, which we bound by bounding the stability of the iterates, where stability of a randomized algorithm M is defined like so, and the supremum is taken over all pairs of adjacent data sets that differ in one data point. The second term corresponds to the private optimization error of our algorithm. So this is the error that our algorithm would incur even if we knew the true data distribution's PI and there was nothing to estimate, and we just needed to privatize the steps of the algorithm. In particular, if d over epsilon squared is less than m, then we see that the dominant term in this bound is the first term, and we're able to match the optimal non-private rates up to log factors. And remember, in practice, we can think of epsilon as being a constant, such as 1. So this, loosely speaking, corresponds to the underparameterized regime. We can also observe that the ISRLDP rate sits between the optimal rates for local DP and central DP, which were known from prior works. So in particular, this is intuitive because we know that ISRLDP is intermediate between these two extreme privacy notions. So we see that we're able to get better accuracy than local DP by relaxing the stringent requirement of local DP, whereas central DP achieves the best accuracy but has the weakest privacy guarantee. And I've only shown you an upper bound on this slide, but I did tell you that the algorithm is optimal. Optimality follows from our novel lower bounds, which I'll talk about next. But are there any questions on the upper bound before I move to that? Yes?
Could you please go to the previous slide, the algorithm?
Oops.
Yeah, notice.
Sorry, yeah, I know. Okay.
Notice there are two parameters, the tau and the n denotes the outer and inner number of loops. Right. So I wonder like how you like can optimally choose the tau n to achieve the optimal upper bound.
So n is given to us. So n is the number of hospitals, and so in every phase, in each phase t, all the hospitals in parallel are going to are going to send or calculate their noisy gradients and send them back to the server.
Oh, I see. So, do you think like for each time, maybe we can first let the hospital to do several times of the local SGD, and then they update their model to the centralized server? Would be better or not?
So that's another algorithm. Yeah, that's like federated averaging or local SGD is another popular algorithm of federated learning that we could try to privatize. So it's usually suboptimal in the non-private literature in the stochastic setting. So that's why I decided to privatize this one instead, because I wanted to start with the accelerated version of this is like optimal in terms of sample complexity for non-private distributed optimization. Whereas federated averaging, like it's an active line of work trying to make it optimal under certain assumptions, third order smoothness and this sort of thing. But in general, it's at the time when I wrote this paper, it wasn't optimal. And we compare against that as a baseline in the experiments, and we outperform it. Okay. So, oops. There we go. Okay. Okay, so lower bounds. So we prove the following lower bound theorem. For any epsilon delta ISRLDP algorithm, there exists a convex Lipschitz federated learning problem instance such that the excess risk of the algorithm M on this problem instance is lower bounded like so. And since this lower bound matches the upper bound on the previous slide, we can conclude that noisy minibatch SGD is minimax optimal for this federated learning problem. For the proof, the idea is to relate ISRLDP to central DP, because lower bounds for central DP optimization were already known from prior work, so we'd like to be able to leverage those lower bounds somehow. In order to do this, we prove the following privacy amplification by shuffling result. We show that if we're given an epsilon 0 ISRLDP algorithm, and then we imagine a random shuffler that receives these noisy differentially private messages and then draws a uniformly random permutation of n, and applies that permutation to the labels of the messages, effectively shuffling them or anonymizing these messages, then when these shuffled anonymous messages are sent to the server for aggregation, from the perspective of a central DP adversary, the shuffled messages will now satisfy epsilon 0 over square root n DP. So this is privacy amplification by shuffling, and this is the main technical component of this lower bound proof. The next two steps with this result in hand are fairly straightforward. So second, we can apply the known central DP lower bounds to this shuffled algorithm, which will give us a lower bound on the excess risk of any shuffled ISRLDP algorithm. And then third, we conclude, we just observed that since the data distribution we constructed is IID, the error of the shuffled algorithm equals the error of the original ISRLDP algorithm. And so the lower bound that we obtain in step 2 applies verbatim to the original ISRLDP algorithm. And that gives us this desired lower bound. Any questions on the lower bound? Okay. So, turning to some experiments. Here we do linear regression with medical insurance data. So the goal in this experiment is to predict medical insurance costs given sensitive patient health records. And on the y-axis we have normalized test error, and on the x-axis we have privacy. Our algorithm is shown in blue, and we compare against several baselines, including 2 non-private algorithms, distributed mini-batch SGD and federated averaging or local SGD. And in yellow is a intracellular level DP version of federated averaging. So FedAv is a popular algorithm for federated learning that's used in industry. And we see that our algorithm consistently achieves superior privacy accuracy trade-offs compared with the other DP baseline. And compared to the non-private baselines, at least on the left-hand panel, we see that as epsilon approaches 3, our performance essentially matches the performance of the non-private baselines. So we're actually getting a strong privacy guarantee effectively for free in this experiment. And in my papers, we have many other experiments on different data sets and different models. The results are qualitatively similar, with our algorithm consistently outperforming the other DP baseline and also getting privacy for free in certain parameter regimes. So the next question is, can we improve over our noisy minibatch SGD algorithm? We show that it has minimax optimal excess risk. It's a scalable first-order stochastic optimization method that permits small batch training, and it has state-of-the-art practical performance in numerical experiments. But I didn't tell you about the communication and computational efficiency of this algorithm. It turns out that a relatively large number of server communications and gradient computations is needed in order to achieve the optimal excess risk bounds. And this can be costly for large-scale problems. So can we design a more efficient error-optimal ISRLDP algorithm? It turns out the answer is yes, and our new algorithm is going to be called Accelerated Localized Phase DRM, and it achieves optimal excess risk with significantly improved communication complexity and gradient complexity compared to our previous algorithm. Looking at these bounds, we see that the communication complexity bound matches the non-private lower bound on communication complexity, suggesting that our algorithm might be not only error optimal, but also communication optimal. However, we can't quite conclude that our algorithm is communication optimal at this point because this lower bound is only proved for deterministic algorithms, whereas our algorithm, like any DP algorithm, is randomized. So something that I'm currently working on is trying to prove my conjecture that indeed this algorithm is communication optimal, and I'm trying to do that by proving a lower communication complexity lower bound that holds for the wider class of randomized algorithms. Looking at the gradient complexity bound, we see that the first term in this bound is typically dominant in most parameter regimes, and by comparison, the gradient complexity lower bound would be NM. So another problem that I'm currently working on is trying to close this gap of roughly NM to the 1/8 by developing a new ISRLDP algorithm that achieves optimal excess risk with gradient complexity, optimal gradient complexity equal to NM. Okay, but enough about future work. Let me tell you about how this current algorithm, which is still pretty good, how this works. So the first ingredient that we're going to need is an accelerated version of the ISRLDP minibatch SGD. So first recall Nesterov. We first take a step of vanilla gradient descent to go from WT to YT plus 1. And then we're going to slide past YT plus 1 using information from the previous iterate YT to guide the direction of our momentum step and get to WT plus 1. This algorithm is optimal in terms of iteration complexity for smooth deterministic convex optimization. In a stochastic convex optimization setting where the population gradient is unknown, we can instead estimate this unknown gradient in an unbiased fashion by drawing a random stochastic gradient. And this leads to an algorithm that's optimal for smooth stochastic convex optimization. Now we can try to follow in this framework in the intercellular record level DP setting by getting a distributed differentially private estimator of our unknown population gradient by averaging noisy gradients across the n silos. And this indeed, by plugging this gradient estimator into the accelerated algorithm, this would give us an ISRLDP algorithm, but unfortunately it has suboptimal excess risk. An important reason why this is suboptimal is because acceleration hurts the stability of the iterates, impeding the generalization error of our algorithm. So can we devise a stable accelerated algorithm that generalizes well? In order to do so, we're going to add a quadratic regularizer to our empirical risk minimization objective in order to enforce strong convexity. And now consider algorithm 1, which is to solve this strongly convex regularized DRM problem using the accelerated noisy minibatch SGD that I described on the previous slide. We have the following facts. One is that if we find an exact minimizer of this regularized DRM objective, then that exact minimizer, W hat lambda, satisfies this stability bound. Okay? So the output of the solution can't change by too much. We also know that if we have a stable algorithm, that algorithm is guaranteed to generalize well, with the generalization error bounded proportionally to the stability bound. We can also prove the following proposition. Algorithm 1 efficiently finds an approximate solution to this regularized DRM problem. So by putting these facts together with this proposition, we can argue that the noisy accelerated mini-batch SGD is stable because it approximates a stable algorithm, and hence that it generalizes well. And so this gives us an excess risk bound for algorithm 1, but unfortunately it's still suboptimal because the private optimization error is too large. But can we use algorithm 1 to build an efficient optimal algorithm? In order to do so, we're going to repeatedly call algorithm 1 with changing parameters in each phase in order to iteratively zoom in on the solution over time. So let me walk you through how this algorithm works. It runs over the course of log m phases, where m is the number of data points per hospital. And so in phase 1, we start with our constraint set and our initial point W0, and our goal is to get close to the unknown optimum. And so I equals 1, so we're going to have each hospital is going to draw m over 2 data points from their local data set. And then we're going to pool these data points together, forming this, this distributed regularized ERM problem. And then we're going to find an approximate solution to this regularized ERM problem by calling our noisy accelerated algorithm 1. And this is going to give us the next iterate, W1. Now, we're going to shrink the constraint set around W1 and shrink the step size and increase lambda I. So the purpose of this is, by shrinking the diameter, we're improving the stability of the algorithm. Okay, so we're controlling the Lipschitz parameter of the regularized loss, and we know that the stability bound scales with the Lipschitz parameter. And to reinforce this localization behavior, we also increase lambda I. So intuitively, increasing the regularization parameter is going to penalize us in the next phase from moving too far away from W1, and hence too far away from W star. So, and formally, this improves stability, hence generalization error. And we're also decreasing the step size for 2 reasons. One is to decrease the scaled variance of the privacy noise, and another is because we're increasing lambda I, we need to decrease the step size for convergence. So now I equals 2, we go back up to the top of the for loop, I equals 2. So each hospital now is going to draw m over 4 data points from their local data set, and these data points are disjoint from the previous data sets, from the previous data points. The intuition here with this geometrically decreasing number of data points is early on we have a very large space, and so we want to use a lot of our data set to explore as much of the space as possible. But in the later phases, you know, our constraint set shrinks, and so fewer samples suffice to make progress. So now we form a new regularized ERM problem using these nm over 4 data points that are disjoint from the previous ones. Our regularization center is now W1, and we're going to again call the noisy accelerated algorithm 1, this time initialized at W1 with our new choices of algorithmic parameters, and that's going to get us to our next iterate, W2. And then again, we're going to shrink the diameter around W2, increase the lambda I, decrease the step size, and we repeat this process for log n phases until we arrive at the last iterate, WL. And we can prove that WL has optimal excess risk and achieves these communication complexity and gradient complexity bounds shown here. The idea of the proof is to use the facts and the proposition on the previous slide in the right way and choose these algorithmic parameters carefully. Any questions on accelerated localized phased ERM?
So intuitively, you adjust this di and lambda I together, well, they seem to have the same effect of, avoiding going too far away from, the previous round optimal value. So what is the intuition behind that? Why they need to be adjusted simultaneously?
Yeah, so good question. As you increase lambda I, you're promoting stability, but you're also increasing that you'd be promoting stability if you fix the Lipschitz constant, right? Because the stability bound scales like L over lambda. But if the problem is that as you increase lambda I, your regularized loss function, the Lipschitz parameter of the regularized loss actually explodes. So you need to counteract that and control the Lipschitz parameter of the regularized loss, you need to, when you increase lambda I, decrease the diameter so that you're only optimizing over a smaller set, and the Lipschitz parameter on that smaller set is actually bounded by L plus lambda I di, so that's why.
Yeah, thank you.
Any other questions? Okay, so to recap what we've done so far, we talked about how federated learning lets multiple parties collaborate without sharing their sensitive data. At the same time, FL model updates can still leak private information to an adversary. And so to address this limitation, we proposed inter-silo record-level differential privacy as a strong practical privacy notion, particularly in cross-silo federated learning applications. Working under the constraint of inter-silo record-level DP, we characterize the minimax optimal error rates for convex federated learning. Our algorithms are not only minimax optimal, but also scalable, efficient, and practical. Now, everything we've discussed so far has been for cross-silo federated learning, where the parties collaborating contain many different data points from many different people, such as patients or students. But in other settings, we instead use cross-device federated learning. This could be, for example, used by tech companies for training large language models on cell phone users' text data. Indeed, companies are using this for that. And so in this setting, we kind of need a different privacy notion, because now one person is contributing many data points. And so this makes that person more vulnerable to privacy attacks, as opposed to the case where a patient is only contributing one medical record and there are many other patients to kind of help protect. So in a different work, I addressed this question of private cross-device federated learning, giving optimal algorithms, minimax optimal algorithms that run efficiently. In fact, for sufficiently smooth loss functions, I obtain optimal excess risk with optimal gradient complexity. And because this privacy situation is a bit more tricky in the cross-device setting, we also need a somewhat more sophisticated privacy technique. So in the cross-silo case, we saw that simple Gaussian noise addition was actually sufficient for privatizing our algorithms and getting optimal rates, but such an approach is actually suboptimal in the differentially private cross-device setting. So instead, we use a differentially private outlier removal procedure to reduce the amount of DP noise that we need to add. And yeah, I'd be happy to talk more about that later if we have time, or in one-on-ones. So returning to the question that I posed at the beginning of this talk, how can we develop optimization algorithms for training ML models that are differentially private without sacrificing more accuracy than necessary? Through this journey, we've seen the complexities of balancing these trade-offs and the innovative solutions that can be used to achieve this goal. However, privacy is just one critical component of trustworthy optimization in machine learning. In addition to privacy, we need to be aware of other essential principles such as fairness and robustness. And my work has analyzed the interactions between these three pillars of trustworthy machine learning and optimization, as well as their fundamental trade-offs with accuracy. Moving forward, I hope to deepen my research in these three areas while also broadening my horizons. So my future work will center around the foundations of trustworthy optimization in machine learning, practical applications, and policy considerations. So first, I'll continue analyzing the foundations of private, fair, and robust machine learning and optimization. And I also want to branch out and start studying explainability, which is the ability to explain how and why ML-informed decisions get made, which is critical in deployments such as criminal sentencing, where transparency is really important. So I'll continue analyzing the fundamental limits of performance for trustworthy optimization. For example, practical DP optimization problems such as bi-level optimization and parameter-free optimization are still open in terms of how much performance we can get for those problems. I'll also explore the interactions between these pillars of trustworthiness, such as the trade-offs between privacy, fairness, and accuracy in machine learning, as well as potential synergies between these pillars, such as between privacy and robustness, where enhancing one of these may help strengthen the other. So in particular, I'll aim to determine the minimax optimal rates for differentially private, robust stochastic optimization. And another area of interest for me is in going beyond the worst case and identifying problem instances that are not worst case scenarios and trying to leverage the structure of these problem instances in order to circumvent the pessimistic minimax lower bounds that we have. For example, can we leverage the structure of neural networks to improve performance in private deep learning and get around the pessimistic lower bounds for differentially private non-convex optimization? I'm also interested in exploring the notion of instance optimality in differentially private optimization. So most of what I've been talking about in this talk has been minimax optimality, where we're looking at the worst case problem instance in a class, but can we develop algorithms that are not just minimax optimal, but actually instance optimal, meaning they adapt to the hardness of the problem, and if I give you an easier problem from the class, their performance should get better. So this is a stronger requirement than minimax optimality, and I think it's sort of a wide open area that hasn't really been, only the surface has been scratched in differentially private statistical estimation, but in optimization we still know very little about this, and it's important in both in bridging theory and practice. And I'll continue developing algorithms that are not just optimal, but also scalable, efficient, and practical. And these foundational insights will inform tailored solutions for high-stakes, data-sensitive domains, such as healthcare, transportation and supply chains, finance, and generative AI, to name a few. For example, can we develop memory-efficient optimization algorithms for fine-tuning large language models privately, so that we can do private fine-tuning on people's devices, for example? And I look forward to forming new collaborations with domain experts in these areas and other areas, and including those in this room right now, and hearing any applications you have in mind for that might require privacy, fairness, robustness, or explainability. And finally, I'll also want to study the public policy considerations of trustworthy AI. For example, the current policy of imposing fines for blatant privacy violations may be inadequate, because privacy violations can be difficult to detect, for example, as we saw in that ChatGPT example. So should differential privacy be required in certain sensitive applications? If so, what epsilon should be required? So I believe this is a question that's going to involve weighing different factors, economic factors, social factors, philosophical, as well as statistics and machine learning methodology. And so I believe that my background with public policy, data privacy, and machine learning will give me a unique perspective to contribute to this interdisciplinary conversation. Thank you.
There were some questions during the talk. Any additional questions for Raj?
I have a couple of non-technical questions. So as you know, there are companies like Axiom and Experian and companies like that that provide valuable data, right, that are used by retailers, for example, to make credit decisions, to do marketing, etc. Insurance companies to look at what type of, whether to even approve a policy or not, etc. So my question is that right now there are regulations in place that kind of limits what type of data that you can do, that you can use, for example, for credit decisioning. So my question to you is that what can that entire third-party data industry do, and what can I, as for example, a insurance company or a retailer can do using this type of methods that you have described here to make better use of that data but ensure privacy and fairness?
Yeah, that's a great question. I think that's definitely an application area that would benefit tremendously from differential privacy. Yeah, because if the current issue, if the reason they're not allowed to use that data now is because of privacy concerns, this would give a provable guarantee that you can use that data. You just have to introduce a little bit of noise, potentially degrade the accuracy of your algorithm a bit. But the benefit is that now you can actually use that data and ensure that the privacy will not be an issue as long as as long as your data is secure. The output of the algorithm is not going to leak anything significant about any individual. So. Does that answer your question,
Yeah,
Ralph?
I guess I was curious about would regulators be convinced with these arguments saying that yes, it is protected? So
yeah, so I mean that's definitely a different story. It's like communicating differential privacy. Maybe the human factors folks would be important to have in that conversation. Communicating the values of it and making sure people understand what is differential privacy, what is it actually guaranteeing. Yeah, so I think that's like in practice right now.
the second question is that the context in which you have done this research is around individual privacy or private data. As you know, in some industries like insurance, it's not just individuals, they also have commercial insurance policies, like for businesses.
Right.
Businesses have their data, right, in terms of how good they're at paying bills, whether they've had delinquencies in payments, bankruptcies. So is that also considered private data? Is there a dimension to your research which might look at commercial data and how those types of data are used? For example, should I lease this space to this business given their history?
Yeah, I mean I haven't specialized to any applications involving that, but I think that the framework is very general and certainly would would be suitable for that.
Yeah.
Yeah, this setting is any data that we have that we want to protect, we can kind of just apply differential privacy.
Very interesting, thank you.
So let me display my ignorance. This is a very fundamental question. So if I understand it, it seems like the epsilon, which is the privacy parameter, applies to the data set, or say in the example you gave with the hospital database, right? So as an individual, as I understand what you taught me about differential privacy, you lighten up the data to achieve that. But what does that ensure me as because it's random, I might be the unlucky individual, or could I be the unlucky individual whose data is not randomized so much that yet someone who's looking for information about me can get that information, although in aggregate there's more privacy than one might, in appearance.
So differential privacy, no. So differential privacy basically provides a strong guarantee that even for the worst case
For
case
any
person
case,
in the
anyone.
data set, yeah. So if I perturb your data by someone else's data who looks almost identical to you, or who looks extremely different from you, either way, that bound on the output, the probability distributions of the algorithm in those two worlds has to be similar, bounded by epsilon. And so as long as epsilon's chosen appropriately, it's a worst case guarantee. So it's that's sort of something that other people contend with from a different angle. Is it too strong? It's sort of this worst case guarantee. But what if I have an easy data set? That's kind of another line of work. But no, it definitely is strong enough for protecting each individual. Yeah.
Thanks.
Yeah. In the first work you introduced, something like you just add some random noise
Right.
to delta f. Just really simple, straightforward way to
Yes.
do it. So is there other way to handle this privacy, like maybe multiply a noise, or maybe plus a noise mapping through a function? Is there other way in the
Yeah.
literature?
Yeah, there definitely are. So this is so gradient perturbation, I would say, is most popular in practice. And when Google and Apple are using it, they're almost always doing that. They're trying to modify optimization algorithms just by perturbing the gradients. But in theory, and also maybe in other applications, there are definitely other techniques. So you could, instead of perturbing the gradient, one naive thing to do would be to perturb the input data itself. This has very bad accuracy many times, but that's something you could do. You can also, there's sampling algorithms where you're sort of sampling from a perturbed distribution that minimizes some score function or some loss function called the exponential mechanism, basically Gibbs sampling, where the sort of the variance of the distribution that you sample from is proportional to epsilon. There's algorithms called objective perturbation, where you can perturb the loss function itself and then non-privately minimize the perturbed objective. So there's definitely many mechanisms.
Yeah, in your proof of the error bounds, do you assume how the perturbed gradient are used in the training? Essentially, just make a simple adjustment of your parameter, or because I can imagine if we train a large language model, those gradient may use the very complicated way, like maybe multiply with other gradient or back propagation. So do you have any assumption how this perturbed gradient will be used in your centralized training algorithm?
No assumptions. We just know that we're adding mean zero Gaussian noise. So essentially we still have an unbiased estimator of the population gradient, right? It's still unbiased because we're not actually skewing it in any direction. We're just increasing the variance of the estimator, basically. So in the simplest case, you can basically just follow the analysis of standard SGD, but argue that the variance is higher. Of course, for the second algorithm, and it gets more complicated, but yeah, essentially you can think of it as a noisier version of SGD, which already has some inherent noise from random sampling.
Okay.
Yeah.
Okay. Sorry, I have a third question. Yeah, you proved your error bound. Your error bound is the best among all those BP methods. So, but the error bound really didn't tell us if the algorithm will perform well in practice, because other algorithm could be fall within this error bound, but have a much more accurate results on average. So